Chemistry. Let's start here with organic chemistry. Organic chemistry is the study of compounds that contain carbon. And this is the chemistry of life because all living things are mostly made up of carbon.
Categories. So let's start with organic. And so organic chemists pretty much deal with anything that involves carbon and hydrogen and kind of the top right of the periodic table. So one of the applications for organic chemistry is the pharmaceutical industry. So any type of pill you've ever had was made by an organic chemist.
And finally, we get to the huge fields of inorganic, organic, and biochemistry. Organic and biochemistry look at the chemistry of living things, and inorganic chemistry looks at everything else, although there is still a large amount of crossover. Organic chemistry looks at the structure and behavior of the molecules of life, which are typically built from a small set of different atoms: carbon, hydrogen, oxygen and nitrogen, plus a few others. Organic chemists also look at making new organic compounds with useful properties. Organic molecules all contain carbon, and the carbon-hydrogen bond is the most common structure in organic chemistry. There are a huge number of applications of organic chemistry in industry: fertilizers, pesticides, lubricants, polymers, and plastics. And in the consumer world, there's fragrances, flavorings and preservatives, and of course drugs in the pharmaceutical industry.
Inorganic chemistry is the opposite of organic chemistry. This is compounds that do not contain carbon, and it's really mostly based on elements that are metals.
Organic chemist. And so let's move on to now inorganic chemistry. So inorganic chemistry is basically everything except the top right of the periodic table, which we already said organic chemists were taking care of. So inorganic chemists are going to study how crystals form and, in general, the properties of metals. So we'll put nice little metals for them.
Crossover. Most of the inorganic compounds that are studied are man-made, and a lot of the motivation is to find chemicals with new properties that can be used in the chemical industry in the wider world. In fact, there are very few areas of human endeavour where inorganic chemistry has not been used in some way. There's medicine and agriculture, special fluids like detergents or emulsifiers, special coatings, materials, pigments, or fuels for many industrial purposes. Within chemical production itself, catalysts are very important as they speed up other chemical reactions. Inorganic chemistry also bleeds into material science, making solids with novel crystal structures like high-temperature superconductors, for example. The list is endless. Now, between inorganic and organic chemistry sits organometallic chemistry. This looks at organic compounds which are bonded with a metal, and are typically used in reactions in the chemical industry, often as catalysts.
Biochemistry is chemistry that studies the chemical processes that occur within living things. Like we mentioned with eating an apple, where our body will take that fructose and convert it into glucose.
Next, let's go to biochemistry. So just like how we could tell from physical chemistry by the name, biochemists focus on biology. And so if we're kind of looking at what's happening in the body, but also in a chemical sense, we're going to be biochemists. And so just as an example of one thing, they like to study enzymes a lot. So kind of how the body does its own little personal chemistry and keeps us going.
Pharmaceutical industry. And finally, out of organic chemistry comes biochemistry, which studies the chemistry of living organisms. Biochemistry studies components that can be inorganic, like water or minerals, but also looks at the biggest and most complex molecules like proteins, fats, and DNA. At the other end, this field also blends into molecular biology, which looks in the finest detail at how life arises out of the chemical processes inside cells. Within biochemistry, there are four main classes of molecules called biomolecules. Carbohydrates are used for structures and storing energy, lipids, which make up fats, Proteins, which are very large molecules made from amino acids that have a huge array of different functions in the body. And nucleic acids that are used to convey genetic information. Research in biochemistry has had a huge impact on medicine, helping us understand infectious and genetic diseases, improving organ and tissue transplantations, working out what's wrong with you with clinical diagnostics, and of course understanding nutrition, looking at the functions of vitamins and minerals in our body. Biochemistry has also been very important for agriculture, studying soils, fertilizers, and pest controls, and there's many other applications.
And then finally, we have physical chemistry, which can be defined as the physics of chemistry.
And so next, let's cover physical chemistry. So as you can probably already guess by the name, physical chemists combine physics plus chemistry. So this means a lot of math, and actually quantum mechanics falls under physical chemistry. So lots of cool stuff there. And just a fun fact, physical chemists are often the nerdiest of all chemists. I personally think it's because they like math so much.
Physical chemistry studies chemical systems in terms of their physics, so things like energy, force, time, motion, thermodynamics, quantum properties, amongst others. There are many subfields, like looking at the electronic properties in electrochemistry, which is important for developing better batteries, or materials science, which is trying to create materials with new properties like extreme strength, durability, or self-healing. This is a critical problem with building Earth-based nuclear fusion reactors, which are reliant on new materials.
The next one here, analytical chemistry, is really a chemistry that deals with careful measurements and trying to get quantitative data. In other words, data that has some numbers.
And keeps us going. And last but not least is analytical chemistry. And analytical chemistry is basically the study of making sure that we do our experiments correctly and the most efficiently. So let's say that we had like a cup of coffee and we wanted to figure out how much caffeine was in that coffee. Then we would have analytical chemists figure that out for us.
Analytical chemistry is like detective work. You've got a sample of something and you need to work out what it's made of and the amount of the different components. Chemists have developed a huge array of techniques to probe and measure different properties of different materials. Traditional techniques involve wet chemical techniques like precipitation, which separates compounds depending on what temperature they evaporate. There's also a huge array of modern techniques like chromatography, where different compounds move at different speeds through a solution and so separate. Or the many different kinds of spectroscopy that can detect materials by shining light on them, or mass spectroscopy, where the materials are flung through electric or magnetic fields to separate them according to their masses. Theoretical chemistry attempts to explain the structures of atoms and molecules and how they interact using mathematical methods. It's very closely related to theoretical physics and quantum chemistry, and often uses techniques in computational chemistry where atoms, molecules, and reactions are simulated in a computer. Now, simulating the proper quantum behavior of anything more complicated than a single hydrogen atom is very difficult / impossible for multiple bodies. So many cutting-edge techniques in computer science are used to try and simulate molecules and how they interact with each other. In fact, this is one of the most exciting applications of quantum computers because they'll be able to directly simulate chemical systems and will help with things like discovering novel materials and drugs and a whole lot more.